Sorry guys, again I did the same error before. I think I know what I'm doing wrong, uh, but I don't want to redo everything from the beginning. So let's see if I can redraw this freaking curve, which is this guy. And then we said that okay, this is the curve that we want to approximate, and we know that with the derivative, with a rough, let's say rough derivative, we can draw this line here, which is a straight line, but we want to approximate the curve. Uh, and I will show you how, hopefully. So we said that this was because we chose delta t, this is delta t, and this is delta y or delta f, whatever. We chose such that it's quite large compared to the variation, the actual variation of the curve, which is in red. But as you remember, what we did with the integration, we just chopped the t line in many bits, okay, small bits, as small as you can get, and then by chopping it this way, we can draw these lines, which are the one that refers to the y-axis, and basically, even though my drawing is horrendous, you can kind of see that these are straight lines, small straight lines with different inclination, each of them. They can be represented as a straight line because we are doing, in each step we are still doing, now let's call it small d and small df and small dt, because the increment delta t now is very small, so it's moving towards a small d. It's called infinitesimal. Don't want to get to the details here, but let's let's stick with it. So big delta is going to be small delta. So it's a small t, and we are approximating our curve with many segments, which is not smooth anymore. It's not really a curve, but the finer we can refine this t-axis, so the smaller we can get this point, the better it is for the approximation of the function. And let's see if this works with the with t equal x squared. What can we do with this? So okay, so let's see if I can do it like so, right? So we know, so what do we know? We know that, so let's try to calculate the derivative of this x square function. So y is equal to, sorry, x squared, t squared function. Okay, so we know what we want. So we know that we do t square evaluated in any point here. Let's pick it a number. Let's call it again 2, just for the sake of it, minus t1 2 squared. Okay, this is the difference in the height of this curve, and we do t2 minus t1. This is the definition that we know of delta f on delta t. Nothing changed. We just pick, if you remember the first slides, f2 minus f1. F is 2, t2 squared, t2 1 squared. So not doing anything special here. I'm just using the same definition over and over. But now we can use the same trick that we used last time for the integral, which I remember here, which is nice. I told you that I like it. So we know that a squared minus b squared can be, okay, no my space. Let's write it like so. A squared minus b squared, if you remember, is a minus b, a plus b. Okay, a minus b, a plus b. A plus b, we know it's always, oh no, but we don't need to do anything here. We don't need to divide. Just plug in this formula here, plug it in here with the correct changes. So we do this, and we write this as, sorry, so t2 square minus t1 square, it's t2 minus t1 divided, multiplied by t2 plus t1. This is exact. It's always true, even when they are zero. So that's okay. We're not cheating. So we draw the line and we do down to minus t1. Now, here is the trick. No matter what tn2 and t1 are, as long as we are able, as long as they're not both zero, I mean, in those cases we need to be technical about it, and I'm not going to do that now. We can just say that this number is the same as this number, so we are allowed to just simplify the number, because I mean, if you multiply and divide a number by the same quantity, nothing changes. In fact, they can simplify, and we know that with this definition, our delta f, so our derivative, if I can write it, delta f, in this case, f, let me write it here, f of t is equal to y, which is t square. Okay, just juggling with letters, but it will make sense, hopefully. This is delta f over delta t, so our derivative is, in this case, t2 plus t1, t2 plus t1. Okay, now if we pick t1, oh, and just a step before, we can think about this as very close, these two numbers very close, t2 and t1, so we can write this one as small delta t, because we are already thinking about limiting procedure. So this is delta t and delta f and delta t small. Okay, and also allow me to just do the same trick. It doesn't change much, but it's to clean a bit the board, the whiteboard. So let's pick t1 always as 0. I mean, just makes things easy. So t1 is 0, so we are left with t2, but in this case t2 can be any, we can shift this graph anything where we want, so let's drop t2 as well. And we know in this case that this is a function t. Okay, you see that it's not, we can write it in blue if you like, but it's not the boring function a, it's the less boring function t, which is a straight line. In this case, it's not a constant, it changes with t. In fact, we called this function gdt in the slide before, and in fact we know the derivative of x squared is, if you remember from school or whatever, the derivative of x squared divided over dx is equal to x. Okay, standard rules, and we just see it here clearly. Okay, so no tricks, no nothing. It's just standard algebra at this point, and a little bit of geometry if we remember the connection with trigonometry and angles and stuff. Okay, so now we see that we can do this for many functions. The math can get complicated. Not always you can simplify things and stuff. But what I want to show you in the next slides is how to reconstruct how to link this concept of derivative. First of all, I will give you the correct definition, at least one definition, standard definition of derivative, and then I will try to make the connection with integrals, because there is a nice link between integration and differentiation, which is basically ubiquitous in math, I guess, and in physics definitely. So I will use it in later videos as well. So let me pause it here, study a little bit because I need to refresh my mind on a couple of things, and then I will do another section. Okay, see you later.